we're going to look at this new family of functions known as the inverse trig functions. See, we were very creative when we came up with a name for this. I mean, exponentials, the inverse are logarithms. And they said, okay, trig, what shall we call the inverse functions for that? Let's call them inverse trig. So they're the inverse to our trig functions. So let's create them. So first of all, we'll look at inverse sine. This, by the way, explains why we have the reciprocal ratios, cosec, sec, and what have you. Because normally, you'll remember with trig, we put the power where this negative 1 is. But that negative 1 does not mean 1 over. It's representing the inverse sine. So you'll never see a trig ratio to the power of a negative indice. They'll always use the reciprocal ratio to avoid any confusion. So negative 1 always means the inverse trig function. So obviously it comes from the sine function. So let's draw up our sine function. We know the domain's all real x. We know the range it goes in between -1 and 1. But it will fail the horizontal line test. So it does not have an inverse. So remember, we want to create an inverse by restricting the domain. And what we said was, we want to get a piece of the curve which is always increasing or always decreasing. So we've actually got lots of choices there that we could do. But our rule of thumb, if you like, we want to include the origin and positives if we can. So it looks like the logical place to do it would be to go from minus pi on 2 to pi on 2. Then from those points, the curve would be continually increasing, and we'd get the whole range. It would still go between -1 and 1. Okay, so how do we invert it? Well, it just becomes y equals the inverse sine of x. Its domain is the range of the sine function, -1 to 1, but its range will be the restricted domain. So it goes from minus pi on 2 to pi on 2. If we were to draw it, we'll reflect it in the line y equals x. Only problem is it's a bit hard to do that on the scale I've done, so I'll actually draw it separately here. So on the x-axis, we'll now go from -1 to 1, and on the y-axis, minus pi on 2 to pi on 2. And there you go, that's an attempt to draw it. Remember, you're drawing a sine curve on its side, so it's not a cubic, it's not a tan curve, but it's a sine curve going sideways. It's just a piece of it. This, by the way, explains why when you put values into your calculator and you're trying to find the angle, the calculator will only give you positive acute angles or negative acute angles. It never gives you an obtuse angle. Remember when we were using the sine rule, we had that problem with, is it an obtuse angle? And that's because your calculator uses functions. So it can only give answers from minus pi on 2 to pi on 2. Okay, so there's our inverse sine graph. Let's have a look at inverse cos, see what happens with that one. So we'll draw up our basic cosine curve. Once again, fails the horizontal line test. Its domain at the moment is all real x, and the range is -1 to 1. But again, we want to pick a piece. I can't use the same one I did for inverse sine, because you'll notice between minus pi and 2 and pi and 2, it's increasing for part of it and decreasing for another. So we want to pick a piece that's always increasing or always decreasing, and we'd like to include 0 if we could, and the positives. So the logical one here would be, we'll go from 0 to pi on this one, and then it's continually decreasing. So our restricted domain, 0 to pi, again we will capture the whole range. So the inverse cos function, the domain, range of the cosine function, -1 to 1. Range will be the restricted domain, so it goes from 0 to pi. Okay, let's draw it separately here. So this time, well, x-axis is the same, -1 to 1. But we'll go from 0 to pi on the y-axis, and it's a cosine curve we're drawing. You've got to be real careful with this one. It's so easy to draw it backwards, but think about the cosine of pi is -1, so it must start over here. So we end up with something like that. So there's our inverse cosine graph, and that's why when you use your calculator, you can get obtuse angles when you're using cosine, because the inverse cosine function goes between 0 and pi. All right, let's complete the set. Let's have a look at inverse tan. So our tan function. So that's the one that alternated between x-intercepts and asymptotes. This function, the tan curve, is always increasing for everything, but we do have those asymptotes as well. So our domain, or real x, accepts pi on 2 plus pi k, where k is an integer. The range is all real y, fails the horizontal line test, and here I guess the logical one to pick is just that branch of the tan curve that goes through the origin. So we'll restrict it from minus pi on 2 to pi on 2. But notice we're not including those because that's where the asymptotes are. And the range is all real y. So therefore the domain for inverse tan is all real x, and the range will go between minus pi on 2 and pi on 2. So this time when we draw it, here we go, we'll end up with horizontal asymptotes at pi on 2 and minus pi on 2, and we'll have that branch of the tan curve going in between. So there's inverse tan. And also explains on your calculator when you're using tan, again, you only get acute angles or negative acute angles when you're using your calculator. So they're the three basic inverse tan functions. So what can we see from those pictures? If you have a look at the inverse sine function, you can see that it does have rotational symmetry. So it is an odd function. Therefore, inverse sine of negative x would be equal to the negative inverse sine of x. Inverse cos, there is a relationship. It's not as obvious when you see it. Inverse cos of negative x is equal to pi minus the inverse cos of x. Now where does that come from? You've got an odd function that's been shifted up pi on 2 units. If you look at your inverse cos curve, it has rotational symmetry, but not around the origin. It's around pi on 2. So that's where we get this relationship from. And I'll explain why in a bit more detail. I think I've got it there in the notes. Inverse tan curve, well, it's got the rotational symmetry. So again, it's an odd function. So inverse tan of negative x is the negative inverse tan of x. And another rule we have here, inverse sine of x plus the inverse cos of x is pi on 2. And that's basically angle sum of a triangle. Always keep in mind that the inverse sine or the inverse cos or the inverse tan, the answer is going to be an angle because we're going backwards, we're getting an angle. So if you were to think of a triangle, one angle, other than the right angle of course, one angle would be the inverse sine of x and the other angle would be the inverse cosine of x. So if you add them up, you must get 90 degrees from angle sum of a triangle. That's where the last one comes from. Well, all right, let's see where this inverse cos relationship is. So there's the inverse cos curve. If I was to move it back down so that we did have symmetry around the origin. So now I'm going to shift the inverse cos curve down pi on 2. So my red curve here would have the equation inverse cos of x minus pi on 2. I've shifted it down pi on 2. Now that red curve is an odd function. So therefore, function negative x would equal the negative of function x. And function x is the inverse cos of x minus pi on 2. So let's sub into that. The inverse cos of negative x minus pi on 2 will equal the negative of the inverse cos of x minus pi on 2. Now, if we play around with this, we should get our relationship. So on the right-hand side, I'll expand the parentheses. And now all I've got to do is the negative pi on 2 on the left-hand side. If I move that to the right-hand side, we get our relationship. Inverse cos of negative x is equal to pi minus the inverse cos of x. That's it. It's not immediately obvious where that relationship comes from. Fortunately, we don't have to do this transformation every single time. We can just quote the result and use it where we need to. But that's where it comes from. You might see some alternative notations for inverse trig. I'm going to say that negative 1, sometimes people confuse it with 1 over. So instead of saying inverse sine is sine to the negative 1, they have this term arc sine. So if you ever seen the expression arc sine, they're talking about inverse sine. And then sometimes people just get lazy and don't worry about the RC. And they'll just say a sine I personally don't think that's a great notation because it looks like you're just saying a constant times sine. And it's pretty rare, the A sine one. But arc sine you do see from time to time in different books. But we'll be sticking with the -1 for the most part. All right. Let's play around with those relationships then to solve some problems. So inverse tan of pi and 3 minus inverse tan of 1. Now you're going to see these numbers crop up a lot because they're the exact values with trig. And remember, we're talking about an angle. So inverse tan of root 3, we're saying, hey, what angle has a tan ratio that ends up being root 3? And minus inverse tan of 1. So we'll get, well, 60 degrees, which is pi on 3, minus 45, which is pi on 4, subtract, and we get pi on 12. Inverse sine of 1 on root 2 minus the inverse sine of minus a half. Okay. Well, inverse sine of a half is pi on 4. You've got to be careful with the negatives. Think of your graph. The inverse sine graph can only give us acute angles or negative acute angles. So the inverse sine of minus a half must be the negative acute angle. And the acute angle that has a ratio of a half is 30 degrees, which is pi on 6. So we end up with pi on 4 minus pi on 6. That turns out to be 5 pi on 12. Of course, the other way you could have done that is you could have used our relationship that we saw and said, well, inverse sine of minus half, inverse sine's an odd function, so that would be the same as minus the inverse sine of half. So you could have done it that way as well. Oh, heck, what's this say? The cosine of the inverse sine of 40 on 41. Remember, inverse sine of something is an angle. So all they're saying is, cosine of this angle, what would the ratio be? Now, it's not an exact one. So what I do with this sort of question is I just draw myself up a right angle triangle. And I'm saying the angle that I'm talking about has a sine ratio of 40 on 41. So I'll say, all right, let's imagine it's this angle down here at the bottom of the triangle. If the sine ratio is 40 on 41, then the opposite is 40 and the hypotenuse is 41. Bit of Pythagoras, and we can find the other side's 9. So now the question is just really saying, what's the cosine of that angle? And I can read it off the triangle. Adjacent over hypotenuse is 9 on 41. So I don't actually need to know what the angle is. That's not what they're interested in here. They're interested in what this ratio is. The inverse sine of the sine of 5 pi on 6. Now be careful with this sort of question, because it looks like they should just cancel, because you've got inverses next to each other. Just like when you say the log of e to the power of something, oh, it just cancels. But we've got to remember the domain and range. Inverse sine can only give me answers that are acute angles or negative acute angles. So it can't give me the answer 5 pi on 6. So what we have to think about is, well, sine 5 pi on 6. 5 pi on 6 is in the second quadrant, which is positive. So should I get an acute angle or a negative acute angle when we're talking about the sine function? I should get an acute angle. So now the question is, well, what is the acute angle when we're talking about the second quadrant of 5 pi on 6? Well, that's just pi on 6. So you need to be real careful with that sort of question, because you have to give it in the correct range of answers. And so for inverse sine, that's going to be minus pi on 2 to pi on 2. Inverse tan, that'll be minus pi on 2 to pi on 2. But inverse cos, your answers will be between 0 and pi. Very easy to do that between minus pi on 2 and pi on 2, because you think, oh, well, the other ones are. Makes sense that this one is as well. But it's not. All right, so let's play around with these new functions of inverse trig.